So we started talking about friction in the previous, not the previous class, I think a couple of classes ago. So we are going to continue with that. So I told you what is the behavior of friction when you have a mass m lying on a rough surface, and you apply an external force P, which is a function of time. In that case, you will have the resistive force friction, which will also be a function of time. When external force P is 0, the friction from the surface on the body will be 0. As you keep on increasing the external force, friction force also will increase. And it reaches a maximum value. So this will be a line. And once it reaches a maximum value, and what is that maximum value? That maximum value is called the limiting friction, and that is equal to mu coefficient of static friction multiplied by n. And what is n? N is the normal force here. Here in this case, that will be the weight of the mass, weight of the object. Once it reaches the maximum value, the object starts moving. This point is called the point of impending motion. The motion starts from here. So once the motion starts, it's easier for you to push the object, and the frictional force value comes down quickly and then reaches a smaller value, which will remain almost the same. Actually, it will have certain other behavior here, but for all our problems, we'll assume that it's same, and that value is called, that value will be equal to coefficient of kinetic friction multiplied by n. T or P. P is a function of T. So that's what I told you. That's what we talked about in the previous class. Just to talk a little bit about what happens, what causes friction, let's go into a little more details. Let's say Let's say this is our mass m, and on this mass we apply the external force P, which is a function of time. Or okay. So why did I draw the surface like this? Why is this curvy? Because no surface can be actually smooth. When we say smooth surface, we assume that friction is zero. But in real life, there is no such surface as a no surface is smooth. There will always be some friction. And when we say rough surface, we are talking about a surface which has relatively large value of friction. So if you zoom into a surface between an object and the ground, at this contact point you will have all these irregularities. It won't be a continuous line. This is not very large irregularities which you can see with the eyes. It's usually microscopic, extremely small. So I have exaggerated these irregularities, the roughness, so that we can study more about the concept called friction. So you need to understand that part. This is not what we see with eyes. Okay, these are microscopic structures. So at all of these points, contact points, it has a mass m. So the total normal force will be mg, and this P, usually the frictional force, value of the frictional force is F, and we will indicate it as one force F. But in reality we usually have this very irregularities in the rough surface, and this F is actually distributed throughout all these irregularities and kind of what do we call it, roughness or something. Let's say this. Each of the small component will have an N1 and an F1. So here also you will have an N2, F2, so etc. Here you will have N3, F3, N4, F4, N5, F5, N6, F6, etc. So there will be very large number of such small components for when the surface is in contact with a rough surface of the object is in contact with a rough surface. But when we solve our problems, we will simply use F. So F is nothing but summation of all these very small Fi's. Okay. Similarly, N is summation of all these small really small values of normal forces. So this is how the friction works. So this is the reason why we have friction. And what will be this what is this component? That is nothing but the sum. I just the sum of these two vectors, let's call it R1, R2, etc. So the total R will be, so these are all vectors. So R vector is nothing but the sum of n vector and F vector. So this is how the frictional force works. So these surfaces, like I told you, we will not indicate what happens at microscopic level in the rough surfaces. We will consider the collective effort of the surface, and we will indicate it as the total frictional force. That is our object, and this is the surface. And instead of writing n1, n2, n3, etc., we will write n. So this is the force from the surface on the object, the normal force. And this is the resultant of n and f. So at the limiting value of f, at the point of impending motion, at the limiting value of f, we know that f will be equal to coefficient of static friction multiplied by normal force. So normal force, so coefficient of static friction is equal to F divided by N, and mu s is equal to tan inverse, wait, mu s is equal to, what is F by N? Let's call this angle theta. What is this angle? This is the angle between normal force and the resultant. If this angle is theta, what will be tan theta? Tan theta will be equal to, if this is F, this will also be F. So tan theta will be equal to F by N, magnitude of F by magnitude of N. So that's what we have here, F by N. So F by N is equal to tan theta. So at the point of impending motion, so you have to note this part, impending motion, or at the limiting value of friction. So this is the case at which this happened, and at that point coefficient of static friction will be equal to tan theta. So this is an important result you need to remember. And now let's say probably to get a better idea of to get a better idea of that angle here, well, another perspective. Let's say you have a mass m which you keep on a rough surface. So this is a rough surface with coefficient of static friction value as mu s. Alright, and m is the mass of the object, and this angle is theta. Let's say you keep on increasing the theta. At the beginning theta was 0, means there was no slant surface. The surface was completely horizontal, and you started increasing this angle theta from 0, 1, 2, 3, 4, 5 degree, etc. gradually. So at a certain value of theta, this mass m will start moving downwards. So this is the point of impending motion. So that is the point at which limiting value of frictional force happens. So at that point, at the point of impending motion, let's say we want to calculate that theta. What is the value of theta at the point of impending motion? So at the point of impending motion, F will be equal to, so what are the different external forces on M then? You will have sorry, not downwards. What is the direction of normal force? Normal force is always normal. You will have mg downwards now we will write only external forces. Why we will not write mg here? Mg is the force by the mass on the surface. So I am going to draw all external force on the mass. So here you will have a normal force N, which is obviously normal to the surface, and F is the frictional force, and friction is equal to coefficient of static friction multiplied by normal force. So this is true only at the point of impending motion. So this is the point of impending motion, and we want to calculate theta at this point. Okay, someone is trying to join. Yeah, and yeah, mg will also be here. Mg is also an external force actually. Mg is the force, gravitational force by the earth on the object, hence it's a external force. So these are the forces we have here. Now from here, how will we calculate theta? How will we calculate theta here? How do we do that? If we the sum of n and f will be equal to, since this is at equilibrium, at point of impending motion the object is at equilibrium, which means sum of all these vectors must be 0, and this angle here is theta, and if that angle is theta, this is 90 minus theta, and this is also theta. If that is theta, if this angle is theta, and if this is this magnitude of mg will be equal to the magnitude of f and n. That is the only possibility, since mg, f and n, for this object to be in equilibrium, that should be the case. So at that point tan theta will be equal to f by n. You can actually see that tan theta will be equal to opposite side by adjacent side, f by n, which is equal to mu s. So the theta here, the angle at which you give the inclination to the surface, tan of that angle will be equal to coefficient of static friction of the surface. So this is something else you can keep in mind. So this is also a very easy way to find the coefficient of static friction for any surface, right? You take the surface, keep an object on the surface. So actually there is no such thing as a coefficient of static friction for a surface. Coefficient of static friction is for a combination of surfaces. The friction acts due to the interaction between these two surfaces. So to find out coefficient of static friction between these two surfaces, you put the object on the surface and you keep on giving it an inclination. At a certain point the object will start having a motion. At the point of impending motion, you calculate theta, find out theta, and tan theta will be equal to the coefficient of static friction. So this is that's about that. And now we'll try to solve some problems. Let's say you have a object, a box, forgot the question. What's the question? You have an object or you have a block, you have a box which has a mass 20 kilogram and a force 80 Newton is applied to the box, to the crate. So the question is, determine if it remains in equilibrium if the coefficient of static friction is 0.3. So that is the question. So how do we find out whether the box remains in equilibrium or not? We can actually find out the minimum force P required to move the object. And if that minimum force is less than 80, we will say that the object is not in equilibrium. If that minimum force required is more than 80, we will say that the friction can handle the external force and the object will remain in equilibrium. So how do we solve this problem? We will, like in the previous cases, like we always done, we will draw all external forces on the object. And write down the equilibrium equations. And we figure out whether the object is in equilibrium or not. This idea actually also involves the idea of moment. So that's why I'm wondering whether to talk about this right now. A moment is something you're familiar with. You already know how to, just like the equilibrium of forces, you will have equilibrium of torques. If an object is in equilibrium, net external torque on the object should be 0. And this is just the torque equation.
Sir, can you explain the torque equation?
Yes, I will do that. I will. So I was just wondering, we will do this first or we will solve this problem after solving some simple problems. I mean, there is nothing to worry about here. These are just 3 equations. You take. I think we'll solve this. Okay, we will fully solve it. No problem. We'll take some time and we'll fully solve it. So here, first what have you done? We have drawn the free body diagram, which means draw all external forces on the object. So these are the dimensions of the object. External forces are, you have external force P 80 Newton on the box at an angle 30 degree, and you have normal force from the surface acting on the object, and you have frictional force F, which is obviously in the tangential direction, the direction that of the surface, and you also have the weight mg. And once you write down all these equations, you have now one problem is that the point at which NC acts, you don't know that. You don't exactly know at which point normal force acts. Usually, if you don't have this external force, you can assume that this normal force acts at the center. But when you also have a second external force, which is in some arbitrary direction, an object has certain size, this becomes complicated. So let's assume that the normal force acts at a point x distance from O. So if you assume so, in total we have 3 unknowns. Why 3 unknowns? P is an unknown, NC is an unknown, X is an unknown, F is P is given, right? F is an unknown, P is given. So 3 unknowns, F, X and N. 3 unknowns can be solved with 3 equations. So equilibrium equations in x direction and y direction are very straightforward. Okay, I'll write down the full equation here. We will take the second picture so that it's easier for us. All right, did you understand how we have written all the external forces here? From here to here, how did we come up with this free body diagram? Do you have any questions here? Yes or no?
No, sir.
No, thank you. So that's not a problem here, right? You simply write down all external forces. P is given. We know the weight of the object, so that multiplied by G will be the external force downwards, which is mass, and you will have a normal force from the surface on the object, that is N. F is the frictional force, which will be in the opposite direction of the external force, and in tangential direction of the surface. These dimensions are given. The dimensions is 0.8 meter long, hence weight should act on the middle. We assume that this is a uniform crate, and this here this distance is 0.2. Now here writing down the equilibrium equations in x and y direction are very easy. Sigma Fx is equal to 0. Net force in x direction is equal to 0. How do we write it out? We consider one by one. P. From P what do we have? P cos theta. Right? P cos theta, let's write 30 itself. P cos 30 will be the component in horizontal direction. Will I give it positive or negative sign? It is towards right, hence positive sign. And from 192, do we have something? No, 196 is completely vertical and you don't have any horizontal component. Similarly, NC is also completely vertical, you don't have any horizontal component. But F is completely horizontal. And I'll write F. And is it negative or positive? It's negative.
It's negative.
Yeah, it is in the direction it's acting towards left. That's it. So sum should be equal to 0. Now similarly, net force in y direction should be 0. So vertical component of P will be P sin 30 and that component is acting downwards, right? Downwards. So that should be negative. And 196 is completely vertical and also downwards. So that is also negative. 196.2. F is completely horizontal, so we don't need to worry about vertical component. NC is completely vertical and upwards. Upwards means positive, plus NC is equal to 0. Now comes the moment part. So moment you have to take about some point. Moment about which point would you like to take? It can be any point. So you can take the moment about the middle point or any corner point, any convenient point. But I would personally recommend you to take a point through which many number of external forces are passing. Because in that case, if you choose a point through which an external force is passing, the moment due to that force will be 0. For example, if you take O, 196.2 Newton is passing through O. So what will be the moment due to the force 196.10 Newton? That will be equal to 196.2 Newton multiplied by the perpendicular distance between line of action of 196 Newton force and the point O. And what is the distance? The distance is 0. So that component becomes 0. But if you take a point other than O, that this component due to this force will not become 0, and that's a problem. That's not a problem, but that your calculations will become difficult. Now here okay. Now let's write down the equation for listen very carefully. This can be a little confusing, but if you listen carefully and do some problems, you'll get it. moment about O. Okay, net moment about O should be 0, and we will consider all forces here. Okay, all forces. Let's start with 196.2 Newton. 196 point. What is the torque due to that force? 196.2. Torque is equal to torque due to a certain force is equal to that force multiplied by perpendicular distance between line of action of force and the point about which you calculate torque. So this force means the corresponding force. Okay, this sentence is not complete. Torque due to this a certain force will be equal to that force multiplied by perpendicular distance between line of action of that force and the point about which you are calculating moment. So you are calculating moment about O, and first force you are considering is this one, weight 196.2. What is the perpendicular distance between line of action of 196.2 and O? What is the line of action of this force? Line of action means this is the line of action, right? This is the line of action of this vertical line is the line of action of this force, and that is passing through O. So what is the distance between this line and O? That is 0, right? That is 0. Now let's consider NC. NC multiplied by perpendicular distance between line of action of NC and point O. What is the line of action of NC? This is the line of action of NC, this vertical line. What is the distance between this vertical line and this point? That is X. Now this is O, and this is this external force NC. And what is the direction of torque? Due to NC about O, this is anti-clockwise, right? So when the torque is anti-clockwise, we will take it as positive. So this is just like the conversion with the force. With the force, when force is towards right, you consider it positive. When force is towards left, you when the force is towards right, you consider it positive, and when the force is towards left, you consider it negative. And here, when the force is upwards, you consider it positive. When the force is downwards, you consider it negative. When it comes to moment, when the moment is counterclockwise, you consider it positive, and when the moment is clockwise, you consider it positive. You consider it negative. Sorry. So counterclockwise is positive. Okay, counterclockwise positive, clockwise negative. uh, here NC multiplied by X. NC tends to rotate the object about O in anti-clockwise direction, right? If you fix the object at the point O, and if you apply NC here, if you fix it here, the whole object is going to rotate in anti-clockwise direction, right? So that's why we say the direction is anti-clockwise. So anti-clockwise, positive. Now consider next force. Next, what will we consider? F. What is the perpendicular distance between line of action of F and O? This is the line of action of F. The perpendicular distance between line of action of F and O is 0. So it doesn't matter whether it is positive or negative. Now this P, you can consider the P together. If you consider the P as one single force, then you will have to find out the distance between perpendicular distance between line of action of P and point O. So the line of action of P will be something like this, and you will have to find out the perpendicular distance between this line of action and the point O. You can do that. That is one way to do it, but that's relatively difficult. So it's easier to split P into two components. We have already done that. You can split P into 80 sin theta, which is acting downwards, and 80 cos theta, which is acting towards right. So that will be easier because we can very easily find out the distance between these forces. So P is the only force remaining to be dealt with, and we are splitting P into two parts. Now we will not consider P, okay? P is already split into two parts. Now let's consider first 80 cos theta component. What is the perpendicular distance between line of action of 80 cos theta force and point O? Can someone tell me? So I'm asking you this question. I've told you a little bit about how to take that distance. Now you tell me what is the distance between line of action of this 80 cos theta force and the point O. Someone in the class try to give me an answer.
Hypotenuse of 0.2 meter and 0.4 meter.
No. Actually, that's where the problem is. Line of action of, don't think about the force 80 cos theta. Think about the line of action of 80 cos theta. Line of action of 80 cos theta is an infinite line which has the same direction as that of the force. It's an infinite line. Okay, the line of action of 80 cos theta. What is the distance between line of action of 80 cos theta and point O? You draw a line parallel to 80 cos theta, that is passing through the point. Length of that line is infinite. That's a long line. What is the perpendicular distance between that line and point O?
.2 meters.
0.2 meter, right? 0.2 meter. Thank you. That's something you need to understand, and this is very, very important. People always make that mistake. Okay, the line of action of 80 cos theta is an infinite line. This is the line of action of 80 cos theta. Okay, this line. What is the distance between this line and point O? That is 0.2 meter. So 80 cos 30 multiplied by 0.2. So that is the magnitude of torque due to 80 cos theta. Now is it clockwise or anti-clockwise? Someone tell me. The torque due to 80 cos theta will be clockwise or anti-clockwise? Will that force tend to rotate the object in clockwise direction or anti-clockwise direction? Think about it. Let's say you are pinning the object about at the point O. Okay, object is like pinned at point O and you are using 80 cos theta to rotate it. So will it rotate it in clockwise direction or anti-clockwise direction? Earlier for NC, it was we thought it like that, right? This is point O, and NC, when you push it here, this is going to rotate in this direction, right? It tends to rotate in this direction. So if 80 cos theta is acting this way, and if the object is pinned at O, in which direction will it tend to rotate? Clockwise or anti-clockwise? No answer. This is point O, right? I am drawing point O here, and your 80 cos theta is passing like this. So this is going to rotate the object in the anti-clockwise direction, right? It's passing through this line, which will rotate in anti-clockwise direction. So this is positive or negative? Anti-clockwise means negative. Now 80 sine theta. Last component 80 sine theta. What is the perpendicular distance between line of action of 80 sine theta and point O? Will someone tell me?
0.4 meter.
0.4 meter. So this is the line of action of 80 sine theta. Distance between this line and point O is 0.4 meter. Now does it tend to rotate the object in clockwise direction or anti-clockwise direction? This is the point. Clockwise, right? So this is just assume that you think about it like this. You pin the object at O and you apply 80 sine theta here, right? If this is acting downwards, this will tend to rotate in anti-clockwise direction, so positive. So that's how you find out the torque equation. So that should be equal to 0, right? So from these three equations you can find out the value of x, and if x is negative, it may not be practical for you to the object will not be in equilibrium because uh, because negative value is not practically possible here. And this will not be in equilibrium, right? F and
Sir, won't the last force would be anti-clockwise?
last force
Sin theta.
last force means 80 sin theta.
Yes, sir.
Yes, it is anti-clockwise.
So then for anti-clockwise it shouldn't be negative.
It is positive. Okay, anti-clockwise. I'll write down here. Anti-clockwise will be considered as positive. Clockwise will be considered as negative. So NC was anti-clockwise, so we took it positive. 80 cos theta was clockwise, so we took it negative. 80 sin 30 is anti-clockwise, so we took it positive. So any confusion here? Any confusion here?
No, sir.
Okay. So why do we take this anti-clockwise positive? That is simply the convention. Okay. We usually when we write the components x and y coordinates, and if you start from x coordinate, if there is a line, this angle is usually considered theta, right? This is usually the starting from here, it's usually the positive value. So this is this anti-clockwise is generally considered positive. That is just the convention. You can, if you want, you can take clockwise positive and anti-clockwise negative. No issue. You will still get the answer, but you should be consistent with your sign convention. Whatever convention you take, stick to it. Don't change it. If you are consistent with the convention, you will get the right answer. So this is how you can solve for all these unknowns. So if you get values, if you get unknown values which make sense, this can be in equilibrium. If you get unknown values which do not make any sense, this cannot be in equilibrium. What do I mean by make sense? In this particular case, it's 1:15. Which class do you have? You have a class right now?
From 2.
For the okay, for both batches. Okay, that's fine. So here in this case, F is 69.3, and what is the question? Determine, that is the only thing we have to do, right? Determine if it's in equilibrium. people still trying to join. I don't know why. They're probably so we, like I told you, we are looking for values which make sense. So what values of x will make sense here? Length, total length of the crate is 0.8, and you have 0.4 towards right from O and 0.4 towards left. And if the x is in within that range, the equilibrium is possible. Otherwise, equilibrium is not possible. Here x, what is the maximum value of x possible? What is the maximum value of x possible here for the object?
0.4.
0.4. Okay, so if you consider this negative, this positive and this negative, the maximum value of x possible for this object for the practical purpose is 0.4, and minimum value possible is minus 0.4. So if your result comes within that range, the equilibrium equations can be satisfied, and this can be in equilibrium. So that's what I told you. So if you get values which make sense, equilibrium equation is possible. If you get values which do not make any sense, equilibrium is not possible. So what will be an example of a value of x that will not make sense? Let's say 0.5. 0.5 means it goes out of the object. So you can't have normal force out of the object, right? Similarly, if it is a minus 0.1, minus 1 or something, and again it goes out of the object. That's also not possible. Here you go ahead and find out all these unknowns and and see whether you get values that make sense. Okay, any questions here? This part, this torque equation part, this is something you need to practice. If you haven't understood it correctly, you need to actually practice and make sure that you really understand it. We will solve more problems on this, especially with torque equation, so that you become familiar with the idea. So today we will stop here. Okay, I'll keep the lecture on the YouTube. You can watch it again. If you have any questions, or you have any questions? Yeah.
Do you have previous year questions?
Previous year questions, I don't think I have it. It's I don't really worry about it. Doesn't really matter. It doesn't really matter what they've asked in the previous year question paper. What you need to understand is that you make sure that you understand how to solve the problem and understand the basic concepts. Nothing else really matter. Any other questions?